Welcome to Lecture 3.1, Fourier series and orthogonality. In a nutshell, a Fourier series is a way to write a periodic function, let's say a 2-pi periodic function, as an infinite sum of sine and cosine waves. To do that, we need to consider the vector space of 2-pi periodic functions, and we need to define a clever way to put an inner product on that space. Once we do that, then we can project an arbitrary vector or function onto an orthonormal basis, which ends up being the sine and cosine waves. So this is an incredible application of the theoretical linear algebra that we've built up onto something that is really useful for scientists and engineers. Okay, let's get started. Let's begin with some history. Ancient mathematicians dogmatically believed that only positive whole numbers could exist. However, using basic arithmetic, they could create the negative numbers and also the rational numbers, which are just fractions. Obviously, now we know of the existence of irrational numbers and things like imaginary numbers, but let's just stick with the irrational numbers. These cannot be expressed as fractions, but there are fractions that are arbitrarily close to them. Specifically, this means that they arise as limits of sequences of rational numbers. For example, the number pi is the limit of the following sequence: 3, 3.1, 3.14, 3.141, and so on. As we know from calculus, an alternative way to express pi is as a series, an infinite sum, which formally we can say is a sequence of partial sums. So here's that series: 3 plus 0.1 plus 0.04 plus 0.001, and we can formalize what an infinite sum means by just looking at the sequence of partial sums. So this is x naught, this is x1, this is x2, x3, and so forth. You've seen this before. I'm not going to spend much more time on it. Many students have a similar epiphany as the ancient Greeks when they learn about Taylor series in calculus. When I say as the ancient Greeks, they knew that the square root of 2 was not rational. It could not be written as a number. But not everyone believed that that meant the number actually existed, because if we can't write it as a fraction, then what was it? So once people realized that there were these irrational numbers out there, then they realized that there's so much more that we could create. Now back to Taylor series in calculus. How is this similar? So the function e to the x, when you first learn about Taylor series, you learn that it is this infinite series of x to the n over n factorial. In other words, it's the limit of the following sequence. So take 1 plus x, 1 plus x plus 1 half x squared, 1 plus x plus 1 half x squared plus 1 6 x cubed, and so forth. That sequence converges to e to the x. The big idea here is that even though functions like e to the x don't technically exist in the vector space of polynomials, we can, for all intents and purposes, treat them like they do. Now maybe I shouldn't say for all intents and purposes, but for many, many intents and purposes, we can treat them like they do. That said, we have to be careful. This is why I just balked when I said for all intents and purposes. I really meant for many, especially regarding convergence. For example, consider the following formal power series. G of x equals 1 plus x squared plus x cubed plus x to the fourth, and so on. That, like e to the x, is a limit of a sequence of polynomials. However, it's not a real valued function on the whole real line r to r. For example, it only converges if x is from -1 to 1. So it's really just a function from this restricted interval to the real line. And you likely know that this is equal to 1 over 1 minus x on that interval. So there are a few little technicalities that in this case we have to worry about, and we're going to do the same thing with sine and cosine waves. Not the same thing, a similar analogy that we'll see. And there are some details that we will gloss over that can be dealt with, but again, the big idea here is for all intents and purposes. Maybe what I really mean here is for all our intents and purposes. Let's recall the definition of a vector space. So this is a set V of vectors and a set F of scalars that is closed under addition and closed under scalar multiplication. The infinite dimensional space R bracket x of polynomials has an infinite basis, set of all powers of x. So x to the k, where k is 0, 1, 2, and so on. In other words, R bracket x is the span of these non-negative powers of x. Now, e to the x is not in this span. It's not a polynomial, but as we said, it is really, really close to these polynomials. There is a sequence of polynomials that converges to it, so for many purposes we can just pretend it's like a polynomial. Now, let's consider the vector space spanned by the following set of sine and cosine waves. So cosine of nx and sine of nx. And here, if n is equal to 0, then cosine of 0x is 1. And we don't include the corresponding sine term because we get 0 for that. Think of these elements as smooth sound waves, the elements in the span of this. So we're always going to get something that's continuous and infinitely differentiable. I mean, I'm not sure what we're going to get, but the elements in here are periodic. So if you go 0 to 2 pi, I don't know, maybe you get something like this. It is going to repeat. This is testing my artistic ability once again. So think of this as a smooth sound wave. Now I want to tie together the space of polynomials and this space of sine and cosine waves. So just like how many functions, such as e to the x, are arbitrarily close to polynomials, there are many 2 pi periodic functions that are arbitrarily close to elements in the space V. Examples include square waves, triangle waves, sawtooth waves, and much more. So a square wave is something like this. A triangle wave is continuous, but there's a lot of different versions of these. We can shift them up, down, left, or right. And then a sawtooth wave is going to be a wave like this, and so forth. So what I want you to start thinking about is it's an analogy, these functions to this space spanned by the sine and cosine waves is just like functions like e to the x are to the space of polynomials. So that's an analogy, and I really want you to grasp that and see that before we move on. Technically, we say that the vector space V is dense in the set of 2 pi periodic functions. Just like how we say the set of polynomials are dense in the space of formal power series. And I know I'm maybe beating a dead horse by now, but like we did with e to the x and the space of polynomials, we can, for all intents and purposes, for all of our intents and purposes, treat the set of 2 pi periodic functions as a vector space with the same basis above, the set of all sine and cosine waves, as long as we allow infinite sums. And when I say for all our intents and purposes, what we're going to do is we're going to define the inner product, and we're going to do things like project and add lengths, or measure lengths and measure angles. So not necessarily every single thing, but the things that we need to do and want to do, we will be able to do. Speaking of inner products, let's go back to our favorite vector space Rn and get a refresher as to what these things gave us. So once we defined an inner product on Rn, we were able to measure the lengths of vectors. So the length or the norm of V is just the square root of V dot V. Measure the angles between vectors. The angle between V and W was the inverse cosine of V dot W divided by norm V times norm W. We can project vectors onto unit vectors. Recall the following formula. If we project V onto a unit vector n means for normal, then that's just V dot n. This is the length of V in the n direction. If we multiply that by the unit vector n, then we get a vector of that length in that direction. Now, even if n is not a unit vector, we can still do this. So we do that by dividing by n dot n. I guess I didn't really need to put that in parentheses, did I? So why do we do that? Well, even though n dot n is the norm squared of n, you can write this as v dot n divided by norm n times n divided by norm n. So if we do that, we get two norm n's here in the bottom, and that's why we get n dot n on the bottom there. And finally, and most importantly, the thing that I want you to remember, take away the most, is that we can decompose an arbitrary vector in Rn into components using an orthonormal basis. So that means that we can write v as a1 e1 plus dot 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 an en, and we often just abbreviate this as an n-tuple, a1 up to an. And recall that e1 was this vector of all zeros and a 1 in position 1. En was the same thing but a 1 in position n, and ei is defined similarly. So here, ai is just the projection of the vector v onto the unit vector ei, which is just v dot vi. And let me refresh your memory that in lecture 1.4, when I introduced inner products, I kind of invented my own convention here that I'm going to use a lowercase projection for the length of v on ei, and I'm going to use an uppercase projection for the actual vector. So let's go back up to here. When I said the projection, this is the projection, this is the vector n, and this is the magnitude of that. So I have been calling this v dot n the lowercase projection of v onto n. I don't know if that's standard, but it's sometimes helpful to speak of both of these things. So I'm calling this uppercase, and that's lowercase. So for example, down here, let's take the vector v. I did this one earlier. 3, 4, 5. I think I actually might have done 4, 5, 3, or 5, 4. It doesn't matter. So this is 3 times 1, 0, 0 plus 4 times 0, 1, 0 plus 5 times 0, 0, 1. And this 3 is just the dot product of v with e1. So this is v dot e1. This 4 is v dot e2. And this 5 is v dot e3. So this is what we are going to do with the space of 2 pi periodic functions. We will decompose an arbitrary periodic function like a square wave or sine wave or a sawtooth wave into the components, which will be sine and cosine waves, using an orthonormal basis, which are those sine and cosine waves. We're going to define an inner product, and this is going to be our formula for the coefficients, is the inner product of that function with that orthonormal, or with that unit vector. Once again, here is how we define an inner product, or generalized dot product, on the space of 2 pi periodic functions. So f dot g is 1 over pi times the integral from negative pi to pi of f of x times g of x dx. Once again, think of this as the continuous analog of, say, the standard dot product, which is v dot w, which is the finite sum from I equals 1 up to n of vi times wi. So here we multiply together the components of the vector and add them up. Here we multiply together the values of the function and add those things up. Here's why this inner product definition is so remarkable. With respect to the inner product that I defined right above, this abstract notion using an integral, the following set, b2 pi, consisting of all cosine of nx's and sine of mx's, and this constant function, is an orthonormal basis for the space of 2 pi periodic functions. Okay, so one quick comment. Why is this constant function not equal to 1? You'd think that 1 would have norm 1. Unfortunately, it doesn't. I think I mentioned this back in lecture 1.4, but let's do it again. So the norm of the function 1, let's do the norm squared. That's the inner product of 1 and 1, and that is 1 over pi times negative pi to pi times 1 times dx. And this is 2 pi over pi, and that's equal to 2. So the norm of function 1 is root 2. So the norm of the function 1, I'll put a hat here just so you can distinguish it from these other 4 vertical marks, is 1 over root 2. So that means that if we scale this function by root 2, right, 1 over root 2, the norm of 1 over root 2 is equal to 1. So the reason why this arises is because it's arguably more natural to do this construction using complex exponentials instead of sines and cosines. And if you do that, then you don't have this asymmetry here with a constant function. And we will do that in a few lectures when we study complex inner products, but for now we'll just stick with the real case. Now that we've resolved this pesky root 2, I want to go back and discuss why this entire set is an orthonormal basis for the space of 2 pi periodic functions. Recall that orthonormal means that these things are unit length and pairwise orthogonal. So we'll start with the cosines. It's easy to verify. By easy, it's a little messy, but it's just basic trig identities that the following formulas hold. First of all, if you take the inner product of cosine nx and cosine mx, that with this definition is just 1 over pi times the integral from negative pi to pi of cosine of n times cosine of m x dx, and that is, you end up getting 1 if n and m are the same and 0 if they're different. We often abbreviate this cases notation as delta nm. This is often called a Kronecker delta, and it's shorthand for this 0 or 1. So this tells us that the set of cosine waves are unit length and pairwise orthogonal. Next, we have to verify that the sine waves are the same. So if you take the inner product of sine of nx and sine of mx, we get the same thing we did above, just with sine n and sine of m. And it's not hard to show that this gives us 1 if these are the same and 0 if they're different. So the sine waves are unit length and pairwise orthogonal. So now we know that this entire set, everything in it, is unit length, and that almost everything is orthogonal. We also have to check that the sine waves are orthogonal with the cosine waves. So that means that the inner product of cosine nx and sine mx, which is this integral, 1 over pi times cosine n sine m, that is 0 for all values of m and n. And technically, you need to show that this constant function is orthogonal to the sines and cosines. That's very easy. Well, we can scale this to just show that the function 1 is orthogonal. Let's just do cosine of x. So if we do that, we get 1 over pi times negative pi to pi of cosine of x dx, and that's equal to 0. It's just an area under the curve argument. We have 1 complete cycle of cosine. Now if we have cosine of nx, we have n cycles of cosine, so we also get 0 just by the area under the curve. And same thing holds with sine waves. So that's why this is an orthonormal set. Now I guess I can't really convince you convincingly that this is a basis. So we would also have to show that this spans the space of 2 pi periodic functions, and it does so minimally, and that's a little hand wavy, though every musician knows why that is true, right? If any sound wave, any signal, whether it's be like jagged or whatnot, can be decomposed into the fundamental frequencies or the harmonics, which are just sine and cosine waves. So that's not a proof, but hopefully it's a somewhat convincing argument, or at least some intuition as to why that is true. It does involve a lot more advanced mathematics. That's beyond the scope of this class. Let's say a few words now about the utility of having this inner product on the space of 2 pi periodic functions and this orthonormal basis above at our disposal. So now we can project vectors, in this case functions, onto unit vectors. So the projection of a function f of x onto u of x is just this inner product of f and u. So that is 1 over pi times negative pi to pi f of x u of x dx. And recall that I'm using this lowercase p projection for this because this is a scalar, whereas the uppercase projection I'm going to call is a vector or a function, a unit vector of that magnitude in the direction of u. So I just stick a u in front. And again, I don't think this is standard. This is my notation to distinguish between these two because sometimes one's more convenient than the other. So this projection of this technique of projecting vectors, we use that for the second bullet if we want to decompose a vector or a function, a 2 pi periodic function, into components using our orthonormal basis above. So these are our components. So we can write any function, 2 pi periodic function f, as an infinite sum of cosine and sine waves, and then a constant term out in front. This pesky 2 here is, you probably guessed, because of this pesky root 2 out here. I'll discuss that in a bit later. And as I said before, this will not arise when we use complex exponentials. But back to these cosine and sine waves. So again, a musician knows that such a function can be decomposed into sines and cosine waves. Here's how to do it. So this an, this is the magnitude of f in the cosine of nx direction. That's just the projection of f onto cosine of nx, which is the inner product of f and cosine of nx. And bn is the projection of f onto the sine nx function. So it's the magnitude of f in the sine nx direction, and that is just the inner product of f and sine of nx. Here is a summary. I don't know whether to call this a definition or a theorem, because it's part of it is the definition of the Fourier series, but it's a theorem because it works, because these things form an orthonormal basis. So either way, let's let f be a piecewise continuous 2 pi periodic function. The Fourier series of f is a way to write f as a possibly infinite sum of cosine and sine waves and a constant function. And the formulas for the an's and bn's, which we call the Fourier coefficients, are given as follows. An is the projection of f onto cosine of nx, which is the inner product of f and cosine of nx, which is just the integral of f of x cosine nx divided by pi, from negative pi to pi. Bn is the projection of f onto the sine of nx function, which is the inner product of f and sine nx, which is that same integral, except we have a sine now instead of a cosine. Several remarks. First of all, these formulas hold for all n, including n equals 0. That's why we have to put a 2 right out here in front. So it doesn't have to be there. We could have just put an a naught or an a naught over root 2, but we put a 2 out here, so the formula for a naught is the same thing, just you have to put in 0 instead of n. Next remark. Even though the vector space spanned by the cosine and sine waves, I think of one as cosine of 0 sometimes, technically only consists of finite sums of these functions. If one allows infinite series, and you need to do that if you want to get piecewise continuous functions like square waves, then this construction up here basically works for these piecewise continuous functions as well. So for example, let's consider a simple square wave, so something like this function here. Maybe it's not quite to scale, so this is pi and this is say 2 pi, and say that this is 1 and negative 1. Let's call this f of x. So f of x is either 1 or negative 1 depending on whether x is between 0 and pi or between negative pi and 0. And then we have to extend this to be periodic. So here I'm just defining it on this fundamental region from negative pi to pi so we can integrate. Now notice I have not actually specified what the function is at the point of discontinuity like 0. So is f of 0, is it 1 or negative 1? Well, it's not going to matter when we compute these coefficients which one we arbitrarily assign. So maybe we can say this, let's put that there and then this there, something like that. However, while it's not going to matter, if we compute these integrals, you may ask, which one is it? So what do we get back when we take the function that is this infinite series where these an's and bn's are defined like this? And it turns out the answer is we actually get is that at these breakpoints, this infinite series actually converges to the average value of the 2 points. So if we were to compute this Fourier series and plug it back in, what we actually get is we get this piecewise function that is defined to be 0 at these breakpoints. And that's something that we can prove. We're not going to do it. I think just knowing what happens is 90% of the important parts. And the proof of the convergence is probably a little bit beyond the scope of the class as well. So that's why I said this basically works, is because this isn't technically a square wave, but it sure looks like one, and outside of a few isolated points, it's basically a square wave. Last comment, at times, it may be easier to integrate from 0 to 2 pi in these definitions than from negative pi to pi. It doesn't matter what our bounds of integration are as long as it's a full cycle. So for example, consider a function where maybe we have a sawtooth wave like this, and that this is 2 pi, and so pi is here and negative pi is here. Instead of integrating over this discontinuity, it's just simply easier to integrate from 0 to 2 pi. We'll conclude this lecture with a brief but important remark that basically says everything we've been doing for 2 pi periodic functions carries over very naturally and in the same way for 2L periodic functions. So I've already told you that I can abuse terminology slightly, and I will do so shamelessly right now, and I'm going to say consider the vector space spanned by the following real value 2L periodic functions. So namely the set of all cosines and sines. So this is a set of all cosines of n pi x over L and sines of n pi x over L. Notice that these things go from, so sine of n of 1 pi x over L goes from negative L to L, and the cosine does so similarly. So it's a little bit harder to draw, but it's like that. So everything works the same way. We define an inner product on this vector space just like what we did before. Just replace the pi's with an L. So the inner product of f and g is 1 over L times the integral of f times g from negative L to L. Now we get the same definition / theorem of the Fourier series. So let's let f be a piecewise continuous 2L periodic function. Its Fourier series is the infinite sum of the following sine and cosine waves and this constant a naught over 2, and the formulas for the Fourier coefficients are once again given by the following. An is the projection of f onto the cosine term. In other words, how much of this cosine term is in this function f, which is the inner product of f and cosine n pi x over L, which is the integral of f times cosine n pi x over L from negative L to L, all divided by L. And Bn says how much of this sine wave is built into this function f. That's the projection of f onto that sine wave, which is the inner product of f and sine n pi x over L, which is the integral of f times sine n pi x over L from negative L to L, all divided by L. So that's a brief crash course to Fourier series and the definitions, and we will start computing them in the next lecture. So stay with us.